Oh, hey everybody. We were looking at question 13 in section 4.3. It says a hot air balloon is rising at a speed of 100 meters per minute. So that's pretty slow. And, well, I don't know. Maybe it's fast. Who knows? Whatever the case. If an observer is standing at 200 meters away from the liftoff point, what is the rate of change of the angle of elevation of the observer's line of sight when the balloon is 600 meters high? Okay, so they're giving you a lot of stuff here. This is 200. This over here is x, which is constantly changing. And they ask us again to focus when x is 600, okay? And they're also telling us that the dx dt is 100. And I'm making that positive because it's growing, all right? The question is what's the rate of change of this angle of elevation here? Okay, so a nice picture of this is going to help you figure all this stuff out. And again, once again we're going to be using the tangent function here. And so this 200 is a static number, so it doesn't change. So I can write it as a 200. This x value changes, and so I'm going to write that right there. And it's fortunate because the dx dt as that we're going to get is given to us, right? And they want to know d theta dt, all right? So I'm going to go ahead and start with my tangent theta equals x over 200 again. So now the derivative, as you know, of tangent theta is secant squared theta, okay? But you would stop there if you were taking a derivative with respect to theta. But remember, we're taking a derivative with respect to time. And so remember that theta is a function of time. And so you have to write its derivative here, okay? You might be saying, well, I don't know what theta is. I don't know what function it looks like even. You have no clue what it looks like, but that's okay. You just know that you have to multiply by its derivative according to the chain rule. And so just write that down. And you're like, oh, okay, I guess I'll just write that down. And then over here, you're going to take this. You're going to do the derivative of x with respect to time is just dx dt. And here you've got a coefficient of 1 over 200. I've kind of decided to write this as kind of like 1 over 200 times x. So I left my coefficient there. And now what's the derivative of x? Well, the derivative of x is 1 a lot of times people say. But remember, that's the derivative of x with respect to x. And here we're taking the derivative with respect to time. And so the derivative with respect to time is dx dt. Now, that's awesome because they tell us that the rate of change of x according to time is 100. And so bang, this number, you can replace it with a 100, which I think I did here. There it is. And my 1 over 200 stayed right there. This is 1 over secant squared because I took this secant squared and I divided it over. Why did I do all that stuff? Because I want d theta dt all by itself. So look at that. D theta dt is what I'm looking for. And sure enough, here it is. It's all by itself. And I'm going to go ahead and solve for all of this stuff. Don't forget that theta is inverse tangent of 600 over 200. How do I know that? Because they're telling me to focus on the moment when the hot air balloon is a height of 600 meters, and we know that this is already 200, okay? You wouldn't be able to tell me the rate of change of the angle unless I tell you to say, hey, I need you the rate of change of the angle at a specific moment in time, okay? And that moment is in time. We don't even know the time variable, but we do know that the height variable is 600, and so I'm going to go ahead and use that there. So I'm going to write inverse tangent of 600 over 2. I just wrote as 6 over 2. And that gets placed into the secant squared. You do all that stuff, and you end up getting over, I think it was 1 over 20 or 1/20th, which translates to 0.050. Don't forget, it says present your answer to 3 decimal places. These guys are really picky on their decimals. So just make sure you're doing those decimals pretty well, okay? Anyway, so there you are. Let's, yeah, have fun with that one.